Infrared or IR spectroscopy is focused on the types of chemical bonds that are present in molecules. A real molecule, like butane shown here, is not a static structure unless it's at absolute zero, but rather a dynamic one. The bonds are wiggling and jiggling, the molecule is undergoing conformational changes, the bonds rock side to side as their bond angles deviate from the ideal, the bonds get shorter and longer, and all of these motions of atoms relative to each other in the bonds translate to energies that are present in the infrared region. So they correspond to colors, if you will, of infrared light. There are three main types of bond stretches and bends that we are concerned with at our introductory level. We're looking for OHs, we're looking for what kinds of CH bonds we have, and we're looking for carbonyls. Now, it's worth noting that the y-axis in infrared spectroscopy is often transmittance, which is the amount of light that is passing through a sample as a percentage of how much goes in. So if we're shining light through a sample and that sample doesn't have any bonds that absorb that light or wiggle or jiggle at wavelengths corresponding to the energy of that light, then the light passes through. If we, however, hit a wavelength or a color of light that corresponds to a bond motion, let's say the wiggle or jiggle of an OH, then that energy is absorbed as it excites the molecule, and we see a dip in the graph of our IR spectra. The x-axis, which is too small to see on many of these graphs, is wave numbers, which are in reciprocal centimeters, and those typically run from about 4,000 on the left-hand side to around 400 on the right-hand side. Now, the absorbances that we're most interested in, again, are those of alcohols, which could also be NHs in amines or the OH of a carboxylic acid. And those are typically broad, intense absorbances in the left-hand quarter of the graph. So an OH or an NH will tend to absorb in this region above or to the left of 3,000. The carboxylic acids tend to be a little more centered around 3,000, which can be a bit of a confusion point because the CH bonds that we're interested in tend to be centered right around 3,000 wave numbers. And so again, the presence of an absorbance here like this would indicate the presence of an OH in the molecule. Now, our CH absorbances tend to be much smaller and sharper, and sometimes they will get lost on the carboxylic acid or even alcohol absorbances. But they tend to be smaller and jagged, and they're going to be just above 3,000 if our hydrogens are connected to sp2 carbons, and they'll be just below 3,000 if those hydrogens are connected to sp3 carbons. The last thing that we look for is a carbonyl, which will tend to be a sharp but very intense absorbance right in the middle of the graph and centered around basically right above where it says wave number on the graph that you can't typically read, but it's usually within about 1650 and 1850 wave numbers. The last region, which actually occupies a large fraction of our graph, most of the right-hand side is referred to as the fingerprint region, which, like the fingerprint, has a lot of complex patterns, and that's why we're not going to spend a lot of time at our level trying to decipher what's in there. You can get useful information out of that, but for us, just like a fingerprint, it is a very complex pattern that's reasonably unique for the individual molecule. We're going to take a look at some sample structures here. We have a ketone, an alcohol, a carboxylic acid, all of which are aliphatic or contain only sp3 hybridized carbons. And we'll look at an ester which has an aromatic ring in it, so that we have both sp2 CHs and sp3 CHs. We'll look at all four spectra. This is the infrared spectra of one of these four molecules. Based on what we've just talked about, see if you can figure out or guess which molecule this IR spectra corresponds to. If we consider the three key regions that we're looking for, this one does have an alcohol or OH absorbance. This broad, deep absorbance here is most likely due to an alcohol. If we look at 3000 wave numbers and what's on either side, notice that the structural features or the absorbances in that region are typically or mostly on the right-hand side. That's going to correspond to the sp3-CH bond stretches. We don't have any sp2 carbons, at least not that have hydrogens. And we'll also note that where our x-axis label is, we have no significant absorbance. Now this little thing here, that's really not enough to be considered a carbonyl. This one is too far to the right, so it's at about 1500 wave numbers, and we really need it to be at least 1650. So we might make note of the fact that we have no C double bond O. That observation rules out basically all three out of four of our structures. Right, the fact that we don't have a carbonyl, 3 out of 4 structures have a carbonyl of some kind or another. And by process of elimination, then, we're left with isopropyl alcohol. Notice that it's consistent in that we have an OH bond that is creating this absorbance, and that we have only sp3 carbon hydrogen bonds present. We'll take a look at another one. See if you can figure out which structure corresponds to this particular infrared spectra. In this case, we don't see an OH bond stretch or bend. If there was something here, it's not going to be these little things. It would be a big absorbance, and the absence of which means we can rule out two of our structures at least. We do, in this case, have an intense carbonyl absorbance right in the middle of the typical carbonyl range. And so we do have a carbonyl present, and that makes sense considering we've already ruled out the alcohol on the basis of the absence of an OH group, so we're left with one of the structures that has presumably no OH, so we rule out the carboxylic acid, and has a carbonyl, so it's either the ketone or the ester. If we look at the absorbances around 3000 wave numbers, notice that most of this appears to be to the right of 3000, meaning that we're dealing with sp3 carbon hydrogen bond stretches. That would tell us that we've got the ketone. Now that's a little hard to see, and so this region takes some practice in getting used to, and it'll help us when we've seen one that does have sp2 CHs, so we know what that looks for. Let's take a look at this example. See if you can figure out which of the 4 structures this infrared spectra corresponds to. We'll note again the absence of an OH group, so we are not looking at our alcohol or our carboxylic acid. We do have a nice strong carbonyl absorbance, so that makes sense for either the ketone or the ester. And now if we look at our absorbance on either side of 3000, notice that we do have structural features both to the right, which is going to be our sp3 carbon-hydrogen bonds, and to the left, which is going to be our sp2 carbon-hydrogen bonds. And we do have both kinds present. We've got sp3 CHs in the methyl, sp2 CHs in the aromatic ring, and so the aromatic ring is going to fit this infrared structure the best. By process of elimination, this then must be the last, the carboxylic acid. See if you can rationalize that structure in terms of the peaks, or rather absorbances, present in the infrared spectrum. Now it's easy to see that we have a carbonyl in this case, and that makes sense given the carboxylic acid's carbonyl. Remember that carboxylic acid OHs tend to absorb right around 3000 wave numbers, and those absorbances are broad, like all OHs and NHs typically are. That fits that pattern, but it's right in the middle of the range where we have our CH bonds absorbing. Now notice that in this spectrum we have a fairly extended series of smaller jagged absorbances that are sp3 CH bonds. They're mostly to the right of 3000, which again is where we typically see the sp3s. And when we look at these two absorbances, we're really looking at the sum of them. So if you were to think of this thing as turning upside down, the green CH absorbances are like trees on a mountaintop. Right, on a level field, we'd see the trees all the same height, but since we're on the side of a mountain, some of them at the peak, or in this case upside down in the valley, are taller than those that are further along the slope. So in summary, we can use infrared spectroscopy to identify functional groups or parts of functional groups that are present in a molecule. We're focused on OHs and NHs, and could be carboxylic acids, the types of CH bonds that are present, and whether or not we have a carbonyl. Sometimes it can be very definitive. We look at a signal in the infrared, like the carbonyl is usually pretty easy to tell. Sometimes, especially like with the CHs, we're not really sure, and so we just have to accept that our clues are not going to be foolproof, but that there is some ambiguity in them.